So now we are given a simply supported beam with point load and a couple of UDL load, and a UDL load with another point load on this simply supported beam. We have a 1 kilonewton point load, 2 kilonewton uniformly distributed load over the span of 2 meters, and 4 kilonewton point load. So what we do here is we first look for our reaction. There's our reaction at B, then our reaction at A. So now our reaction at B, to find for the reaction at B, our reaction at B is the bending moment. Reaction at B is the bending moment divided by total length. So we have our reaction at B. We have our reaction at B times what is our total length? 1 plus 1, 2 plus 3, that is equals to 6. It will be equals to, we have the bending moment that is 1 times 1 here, that is 1 times 1 plus this one now, which is the shearing force. Now remember, in a UDL load, I mentioned that in a UDL load over a span X here, if you have a UDL load of W over a span X, the after finding for the shear force will be equal to W times X, as we know. Then the the bending moment, in order to calculate the bending moment, we are going to be putting this shearing force and calculating the distance from the centroid. That is, if we have this load right here, we can imagine it as a point load at the centroid of this, and the centroid of a uniformly distributed load is at the half point. So this, it will be at x over 2, that is half of this entire span here. Just imagine it as a point load, that is the shearing force will be imagined as a point load. So if you are to calculate the bending moment, we have Wx times x over 2, which will be Wx squared over 2 right here. So that's how we are going to calculate here. But right here we have 2 times 2, which is the shearing force, times the distance from the centroid, which is from the center of this, we have 2 divided by 2, then we have plus 1 plus 1, that is plus 2 right here. And continuing, we have 4 here times 1, 2, everything here, that is plus 4 times 5, which will give us 1 times 1 is 1 plus 4 times 3 plus no, this this 4 times 5 here. 4 times 5 here is 20. So if we add all of this together, it will be equals to 33. That is RB times 6 is equal to 33. So if we divide both sides by 6, our RB should be equals to 5.5. So with all this calculation, we have our RB as 5.5. Let me write it here. We have our reaction of B is equals to 5.5 kilonewton. So that is our reaction of B. And then our reaction of E is equals to the total shearing force minus our reaction of B. And the total shearing force here is, in brackets, let's put 1 plus 2 times 2, which is this times this shearing, then plus 4 minus our RB. So this is equals to, we have 1 plus 4 plus 4, that is equals to 9, minus what is our RB? 5.5 kilonewton, which will be equals to 3.5 kilonewton. So that is our reaction. That is our reaction at A. We have our reaction at B and our reaction at A. So since we have gotten our reaction, we can be able to solve for our shearing force. So now our shearing force at point B here would also be equal to the reaction, because we do not have an external force and this is not an overhanging beam. So our shearing force at B will be equals to 5.5 kilonewton. Now our shearing force at F here, at F, would be equals to this shearing force, the this one 5.5 minus, because this one is pointing downward, minus 4 kilonewton, minus 4, which will be equals to 1.5 1.5 kilo Newton. That would be our shearing force here. So then our shearing force at E, our shearing force at E would also be the same thing. So we can actually say that our shearing force at E here is still the same thing, because the bending moment from the shearing force from here is calculated at 2 times 0, because it is not moving at all. So our shearing force at F is the same thing as the shearing force at E. Yes, the shearing force at F is equals to still the same thing, 5.5 minus 4, which is equals to 1.5 kilo Newton. Then our shearing force at D right here. So our shearing force at D would be, our shearing force at D right here now would be equals to, we have this, which is 5.5, then this point load minus 4. We also have minus this here, which is minus 2 times 2, which will eventually give us 5.5 minus 4, 1.5. 1.5 minus 4, we have minus 3.5. We have minus 3.5 kilo Newton, which will eventually go to the end. We also have S of F at, we have S of, it is supposed to be minus 2.5. Yeah. If we minus this together, we have minus 2.5. So then we have our S of F at C. Our S of F at this point here, yes. So our S of F at C will be equals to 5.5 minus 4 minus 2 times 2, which is this, then minus 1, which will now give us minus 3.5 kilo Newton. This minus 3.5 kilo Newton also matches with our reaction at A, so that is S of F A is equals to minus 3.5 kilo Newton. It also matches with it. So we know that we are correct as far as we have gone. So now moving on to the bending moment. Now the bending moment at B would be equals to 0. Bending moment at B will be equals to 0 kilonewton meter, because there is no reactions, there is no moment, there is no moment acting there. So now we have our bending moment at point F. Our bending moment at point F will be our reaction times the distance between that reaction. So our bending moment at F is 5.5 times 1. We have 5.5 times 1, which is 5.5 kilo Newton meter. So then our bending moment at E here, our bending moment at E would be equals to, we have reaction B, and the distance from reaction B to E is 1 plus 1, which is 2. We have 5.5 times 2, then minus, because this is pointing downward, 4 times 1, 4 times 1, which will eventually give us 7 kilo Newton meter. That's what it will eventually give us. Then we also check for our bending moments. Our bending moment at D here. Our bending moment at D would be equals to, we have 5.5 times, now what is the distance? 1 plus 1 plus 2, that is 4. Then minus 4 times 1 plus 2, that is 4 times 3. Then minus the bending moment of this, minus 2 times 2 square all over 2. And our answer is going to give us, our answer is going to give us 6 kilo Newton meter. Now, between this 7 and 6, we know that we are going to have a point. we are going to have a point there whereby we are going to get our highest value, we are going to get our we are going to get the highest value, like our highest value between this UDL and between these UDL points, and it's most likely going to be at the middle span based on the UDL that we did earlier, because it's exactly at the center of the whole span, so it's mostly going to be at L over 2, but we are still going to check about that. So we have the bending moment at C. The bending moment at C here, we have 5.5 times the distance from here to here, that's 5.5 times 5 minus 4 times 4. And we have minus 2 times 2. Now, in this case, we have a different scenario. 2 times 2, open bracket, 2 over 2 plus 1. That one is the extra value that we are seeing here. So we have this one, and the answer of this would be equals to the answer of this would be equals to 3.3 kilonewton meter. Mm, the answer of this would be equals to something like 3.3. Let's check it. We have 5.5 times 5, 3.3 kilonewton meter. So then we also have our bending moments at A will be equals to 0 because it is at the entire reaction. So now let's check for that max point, the point between this UDL whereby the the bending moment will be the highest. And remember I said that the bending moment, where the bending moment is highest, the shearing force is always equal to 0. So we are finding for S of f of x, where if S of f of x is equals to 0, so that means the shearing force is equal to 0. That means shearing force, if it's equal to 0, that means we have reaction from B, we have the reaction from B, which is 5.5. We have 5.5 times, we have 1 plus 1 plus x. Let x be the distance from here to somewhere here. So we have 2 plus x 2 plus x right here. Then we also have plus our 4 here. 4 times 1 plus x. 1 plus x. X is the unknown distance. Let's say something like this. This is the distance of x that we are talking about here. That's what we are looking for. Then we also have from here, no, it's also 5.5. This one will be negative. This will be negative since it is pointing downward. We have minus here again, minus 2 minus 2 times this is shearing force. This is not the shearing force. We are calculating for bending moment. Calculating for shearing force, we are only going to be considering the force. So we have the shearing force to be equals to, we have our RB, which is 5.5, yes, minus this one, which is 4, then minus this one right here, which is minus 2 times what is our distance, x, minus 2 times x is equals to 0 right here. So that is what it will be. So we have minus 2x, we have here 5.5 minus 4, we have 1.5 minus 2x will be equals to 0. We have 2x will be equals to 1.5 by collect like terms, and we divide by 2. We divide by 2, we have our x is equals to 0.75 meter. So our x here is 0.75 meter, not L over 2 as I have mentioned earlier. So the point whereby the thing is highest is 0.75 meter. So if we calculate our BM max at x is equal to 0.75 from E, that is it. So we calculate our BM max. our BM max should be equals to, we have RB times everything here. Our RB now will be 5.5 times, we have 1 plus 1 2 plus that distance s which is 0.75, that is 2 plus 0.75, that is times 2.75. Then we have minus 4 times 1 plus 0.75, that is 4 times 1.75. Then we have for the bending the UDL, we have minus 2 times 2 times 2 times 0.75. 0.75 is the value of x here. We have 0.75 square all over 2. So if we calculate the bending moment of this, we are going to have a final answer of 7.56 kilonewton meter as our answer. So that is going to be our final answer for this. So now moving on to the bending moment and the shearing force diagram. Moving to the diagram. So let's say we put our dotted line this here, and this here. So now for the shearing force diagram, I'm going to draw a neutral line right here. That is a neutral line of 0 0, that is 0. So our shearing force at B is 5.5. We have our 5.5. We draw it straight here. 5.5, 5.5. Then our shearing force at F and our shearing force at E is um 1.5. So we come down to 1.5. From here to E, that is 1.5. So now our shearing force at D is 2.5, but this is a UDL, so it will be a diagonal line, a 1 degree line. Yeah, let's say we have it that is 2.5, so it will be like this. We have 2.5. Then this drags on to C. We have here, we have 2.5 here, which is 3 point. This one here is 3.5 kilonewton, 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 and kilonewton. This is positive and this is negative. So this is our shearing force diagram for this right here. Now to our bending moment diagram, we put our zero line here. That is, our bending moment at B is 0. Our bending moment at F is 5.5. So 5.5, this would be a straight line, that is a 1 degree line. Then our bending moment at E here is 7. So we can say 7. This is 5.5 kilonewton meter. Here can be 7 kilonewton. Here is 7 kilonewton meter. Then at D here we have 6. So let's say this is 6, but this is going to be some kind of graph. Let me trace this point down here. So now this point here is where it is going to be the highest. This is going to be like a curve. So this point here now is the highest point of that curve, which is 7.56 kilonewton meter, and this is 6 kilonewton meter. So this is 6 kilonewton meter. Then we also have at C, our bending moment at C is 3.3. We have 3.3 here. Newton meter. Then from here to here is 0. So this is the bending moment diagram. Everything here is positive. The bending moment diagram for this load right here.